Would you like to come in and watch a talk? Just about to start, 20 minutes? Okay, well the talks are in here every half an hour, so.
Okay. Whenever you're ready.
Hamza, I want to speak. Ask Pepper. Asked her that question. Hi.
Oh, are you guys, that is very interesting, but if you want to sit down for the talk, that's very good. So hello, my name's Katie, and I'm here to do a talk this morning. So I guess welcome to Peterborough STEM Fest. I'm not one of the organisers, but I am very excited about this. There seem to be so many fantastic things going on today, and I'm very happy to have been invited to come here and do a little bit of a talk for you guys this morning. It's nice to see we had 4 people for a while, but now we've got a fairly decent crowd in, so that's looking good. So I should introduce myself first of all. My name's Katie and I am a mathematician, and what that means is that I studied maths at school, as some of you that are here are probably still currently doing. I went to university and studied maths at uni, and when I finished uni I decided I still hadn't had enough maths yet, so I carried on, did a little bit of research into maths, and now a large part of my job is to come and talk about maths in various different situations. So I go into schools, I do things at science festivals like this, I talk about maths on the radio, on YouTube, basically anywhere that people will allow me to come and talk about maths, I will do that. And from that you should probably gather that I'm really into maths. So I've brought along some maths to share with you guys today. Hopefully you are all either indifferent or positive about maths. I think it's a subject that sometimes gets a bit of a bad rep, so I've brought along some of my favourite bits to share with you on the theme, as you've seen in the programme, of the maths behind board games. And what I'm essentially going to try and do is to tell you about some different ways that you can use maths and your understanding of mathematical ideas to maybe make yourself better at board games, maybe win more often. Maybe see if you can improve your board games, because there are some really interesting things that you can use. Now, the first thing I wanted to talk about was there is, in fact, a whole area of maths, which is, in fact, it's quite a recent area of maths. It hasn't existed for as long as maths has existed, but it actually only came in the last 50 or 60 years. And in fact, if you've seen the film A Beautiful Mind, you might have heard of a mathematician called John Nash. And in fact, it was Russell Crowe in the film playing John Nash, and he was actually one of the people who first kind of came up with this area of maths, and it's called game theory. And it's literally the maths of the way that people make decisions when they're playing games or when they're in kind of decision-making situations. And of course, a lot of the ideas in it are based on very simple kind of game scenarios, but a lot of it can be applied to things like economics, to the way that different countries are going to behave when they're kind of politically discussing things with each other. And you can use a lot of these ideas in kind of much more complicated and important situations. But I'll give you a simple introduction. So for example, just as an example, if you have 2 cars driving along a road, a red car and a blue car, and they're driving towards each other, facing each other, driving along the road. And I guess let's assume, rather than this being a road in the UK or in America, it's a road somewhere kind of completely outside of the rules of law. So each of these 2 drivers that's driving cars has a decision to make. And in fact, the person in the red car can decide whether they would like to drive on the left or to drive on the right, because it's a 2-lane road and they're both driving along it. And of course, we can actually work out what will happen if the red car makes this decision and if the blue car makes a similar decision. So for example, if the red car is driving on the left and the blue car chooses to also drive on the left, they will be, as in the UK, on the correct sides of the road. Everything is fine. But of course, if you're in the situation where the blue car is driving on the left and the red car is driving on the right, because they're facing each other, they're both on the same side of the road, bad things. So again, you can put another row down here for what happens if the blue car decides to drive on the right, and I'm hoping you can work out that the 2 entries in that column will be the other way around. But this is what's called a payoff matrix. And it's a way of kind of putting down all of the possibilities, all the possible different outcomes that could happen, and you can write in the box what will happen in those situations. So this is a very simple example, and I guess each of these drivers has a decision to make. I think they would probably prefer to be in this box or this box. But in order for that to happen, they both need to make the same decision. So it's not as simple as one of them going, I'm just going to drive on the left, whatever the other person's going to do, because it will depend on what the other person's doing as well. And in fact, if you've seen any of these before, you might have seen them in reference to a particular kind of toy problem from game theory, which people often talk about. But I'm going to give you this example because there is in fact a TV game show which is just this example from game theory, and it's an example called The Prisoner's Dilemma. But the game show is actually called Golden Balls. So this is a little bit of a clip from it. It's hosted by Jasper Carrott, who is a fantastic comedian and apparently now hosts a quiz show, although I'm not sure if it's even on anymore. It was a little while ago. But essentially, you've got two contestants and they can choose split or steal. So they've got some money that they've won as part of this game show, and they each have to choose whether to split the money or steal the money. And the way that the situation works is, you can imagine you've got one of these payoff matrices, that if both players choose to split the money, they will split the money between the two players. If one of the players chooses to steal, they will steal it and they will get all the money. But if both players choose to steal, no one gets any money. So it's kind of a bit of an interesting psychological problem. And in fact, if you're wondering why I'm talking about this in a talk on board games, there is a board game of this. So it is completely valid. And in fact, the payoff matrix for this looks like this. So if both players choose to split, they get half each. If red chooses to steal, but blue put down split, red will get money, and vice versa in this direction. But then if they both choose to steal, there's no money for anyone. And one of the nice things about this is called the prisoner's dilemma, because the original kind of statement of this was that you have two prisoners and they're both kind of imprisoned for this crime. And if one of them decides to snitch on the other one and say, oh, well, he did it, then he will get away and the other guy will take the punishment. But if they both say, well, he did it, then obviously they're both going to get punished. So, this is the kind of bad corner situation over here. And in fact, in this situation, one of the things I like about this is that obviously this is the best scenario. This is kind of everyone gets half the money. This is the nicest thing to happen. It's kind of what you would think people would want. And in fact, if you asked anyone about this kind of objectively, they'd say obviously this is the best scenario. Everyone gets some money, everyone's friends, it's lovely. But if you're in that situation where both the players have decided they're going to split the money, there is literally no reason for the red player not to switch to steal, because that would just mean they will get more money. But at the same time, there's literally no reason why the blue player wouldn't switch either. So kind of one of the things about game theory is that you kind of assume that everyone is rational and intelligent and they understand what's going on, but you also assume that they want to get the best possible outcome for themselves. And so the logical thing to do in this case for everyone is to switch to steal, even though if both people do that, it will end up badly for both of them. So it's what's called an unstable equilibrium. Like, you're in this situation where everything seems to be okay, we're going to split the money, we're going to get half each, but there is no reason why anyone would want to stay in that situation. So it becomes an interesting kind of psychological thing. And in fact, you can see a little bit of this in some board games. And it doesn't always apply because the situation has to be just right. But as an example, there's a board game that I'm a big fan of, that I often play, which is a game called Carcassonne. And if you've seen it, it looks like this. You end up with these little tiles. You take it in turns to play tiles on the board, and you place the little men on there as well. And you end up with, you make little cities, you make little roads, and you score points when you finish the thing. So, for example, we've got this road coming down here with a blue player on it. And if that gets finished, if someone places a tile in there, the blue player would score points for that road. And similarly for these little cities, the reason it's called Carcassonne is because they're modelled after the French city of Carcassonne. But it's actually quite a fun game because it does get a bit competitive. You can see we've got kind of 4 or 5 different players here, and they're all competing to try and score points for all these different things. And one of the rules of the game is that if someone's already got a player, if they've already got a little meeple character in one of the cities, you can't add another person to the same city. So you couldn't build an extra piece of city on here and put a person in it because there's already someone who's claimed that thing. But there are other things that you can do. So for example, if the red player has a person in this kind of tiny little bit of city here, the blue player can't actually build on it, but he can start another city over here, which isn't actually connected to it. And now if they do get joined up, both players have that city, so they would now both score points for it. And if you have a situation like this in a game, what sometimes happens is that maybe the red player might kind of build another bit of city over here that's not quite connected up, and then it would eventually get joined on. And now there are 2 red players and 1 blue player, which means red would get the points for this city. So maybe then blue would try putting in a piece over here, and then that would get joined on as well. And essentially, this is going to keep happening because now both players, they've invested some time and some people into this city. And if the other player gets all the points for it, then all of that was wasted effort. So you kind of find yourself locked in these little kind of battles of increasingly putting your resources into something. And you kind of have to step back from it and say, okay, but if I just hadn't done that in the first place, it wouldn't have been a very big city. Whereas now it's going to be quite a big one. It's going to be quite a lot of points for whoever gets it. And you kind of have to think about it in that kind of game theory logic way, like, is it worth investing this time and effort into this? So you can use that kind of thinking. You can think about what the other person's priorities are, what they're going to try and do, and use that to make decisions about how you're playing. Okay, so there is another area of maths that you can use to kind of understand a little bit about board games, and that is to do with probability. Because this is something that if you study maths at school, you'll quite often end up studying things like flipping coins or rolling dice. And in board games, obviously, you end up rolling dice quite often. And I guess the question is, can you use probability? Can you use your understanding of this kind of maths to improve your board game playing? So I guess if you have a dice, like this is just a standard 1 to 6 dice, the probability of rolling any particular number on that dice is just 1 out of 6. Each of these is equally likely, and there is a 1 in 6 chance that you'll roll any of these numbers. And hopefully this is something that's quite easy to understand. But then there are often games where you end up rolling 2 dice. You'll roll 2 dice at the same time and you add together the score. And if you do that, you get a little grid like this. So if you roll a 1 and a 3, then your total is 4. And if you look at this, you can first of all make some nice deductions about what's likely to happen. So if you're playing a game like Monopoly, where you roll 2 dice and you move around the board, if you look at this, you can actually see that the most likely result you're going to get is a 7. Because there are a lot of ways to make 7. You can do it with a 3 and a 4, or a 5 and a 2, or any other different things. You're very unlikely to get a 12, and you're also very unlikely to get a 2, but you're quite likely to get a 7. So you can maybe look at the spaces that a 7 moves ahead, see what's there, maybe work out what you're going to do based on that. I'm going to give you a little puzzle to do. I'm going to give you a little 1-minute puzzle. So I'm going to put 2 possibilities up on the screen, and I want you to see which one, maybe not even calculate anything or work it out, but just use your instinct. Which one do you think is more likely to happen? So the 2 situations are, first of all, you're rolling 2 dice and you're going to try and get a 6. So if either of the dice come up as a 6, then you've succeeded. Or you're rolling 1 dice to try and get a 5 or a 6. Okay, so I'm going to give you 1 minute, discuss with the person next to you, which of these do you think is more likely? Go. Okay, hopefully we've had a chance to chat that through and make a decision, and hopefully you've all come to a conclusion one way or the other. So these in some ways seem like quite similar things, because in the top example we're trying to get a particular number and we've got 2 chances at doing it. We've got 2 dice. In the bottom one we're trying to get one of 2 numbers, and we've only got 1 dice. So it kind of seems like the same thing, but in fact if you look at this grid of possibilities, so if you roll 1 dice and try and get a 5 or a 6, that's a pretty obvious probability, because it's 2 out of the 6 options, so it's 2 in 6, which is a third. In the case of rolling 2 dice and trying to get a 6, these are all the possibilities that will happen. But in fact, these are all the ones where you've rolled a 6 on the red dice, these are all the ones where you've rolled a 6 on the blue dice. There is actually a little overlap there. So the situation where you roll 2 6s only happens once. And in fact, that little overlap means that this is only, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 36, which is actually slightly less than 1/3. Because you've got this particular case here, if that comes up, you still only win once, even though you've rolled 2 6s instead of 1. So in fact, this one is slightly more likely to happen than the other one. And if you understand this kind of slightly subtle little problems in probability, if you're playing a game like, for example, Yahtzee, where you're rolling dice and you can sometimes choose, do I pick up this 1 dice and roll it again, or do I pick up 2 dice and roll them both, and I'm trying to get this thing. If you understand what the probabilities are, you can see which one is more likely to result in success. And I know some mathematicians who play Yahtzee, and it gets very involved, it gets very serious, because they know exactly what is the more kind of like sensible strategy. They know which one is going to give them a higher probability. Obviously, probability things do go wrong a very predictable amount of the time, so obviously they don't always necessarily win on this, but you can improve your chances by thinking carefully about what's happening. Okay, so there is one more area of maths that I wanted to discuss. I think because I didn't start quite on past, I may kind of end up going all the way up to 11 with this. Unfortunately, there may not be time for any Q&A at the end, but I will be around for the rest of the day, so if you do want to come and talk to me, I will be around doing various different things. So there is a whole branch of maths, and it is actually an area of maths that I really like, and I think it's a shame because you don't actually study this very much at school. You maybe do little bits of it, but once you get to university, this becomes a real kind of area of maths that you can actually study, and it's a thing called combinatorics. Okay, and I guess the way to define it, I guess it's like counting but harder. So you're essentially looking at all of the different ways that you can combine things. You're looking at different ways of ordering and combining and sorting things. So as a really nice simple example, if I have 3 things, say if I have the numbers 1, 2 and 3, you might ask yourself a question like, how many different ways can I order those 3 numbers? How many different orders can I put them in? Because I've got 1, 2, 3, I could put 2, 3, 1, I could put 3, 1, 2, like how many different possibilities are there? And in this case, these are all of the different possibilities, these are all the different ways to order 3 things. And if we want to calculate this, it's actually quite a nice calculation, because what you say is, okay, if I'm choosing what my first thing is, I have 3 choices. Right? It can be 1, it can be 2, it can be 3. So I have 3 choices for the first thing. But once I've picked that, I then have 2 choices for the second thing. And once I've picked that, I only have 1 choice remaining. So in fact, I can do 3 times 2 times 1, which gives me these 6 possibilities. And that's kind of, it makes sense when you look at it like that, but essentially you've got 3 choices for this thing, 2 choices for this thing, and then there is only 1 choice remaining for that thing. And this is quite a small example, so you can see it's not hugely complicated, but if you've got, say, 9 things, then the total is 362,880 different ways to order them up, so it grows quite quickly. And in fact, we have a nice little bit of maths notation for this, so instead of writing 3 times 2 times 1, you can write 3 and an exclamation mark, and this is called factorial. If you see someone write an exclamation mark like this, it's not just that they're really excited about the number 3, it is that they want you to take 3 and multiply it by all of the numbers smaller than 3 going down. So for 3 factorial it's 6, for 9 factorial it's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and that will give you your 362,880. So this is a very simple kind of thing that you can calculate. There is another slightly more complicated thing you can do, which is if you have, say, a stack of 5 cards or 5 objects of some description, and you want to choose 3 of them. So I'm going to choose those 3, say, for example. And you could ask the question, how many different ways are there I could have done that? How many different possibilities are there for what those 3 cards are? And in fact, this is a mathematical function as well. And because mathematicians just like to name things, as they are, it's called choose. How many ways are there to choose 3 cards? The answer is 5, choose 3. And this is a function. In this case, the answer is 10, and I'll go through why that is. So it's kind of similar to the previous one. So we start off with 5 cards, and I can choose any one of those 5 cards. So I have 5 possibilities for my first choice. I then have, once I've picked one, 4 possibilities for my second choice, and I then have 3 possibilities for my third choice. And when I've done 5 times 4 times 3, I have picked my 3 cards. But it's not quite that simple, because when I pick those 3 cards, I could have picked the same 3 cards in a different order. If I'd picked out this card first, then that card, the result is the same. So I need to make sure I'm not counting all of those different possibilities more than once. So I now just need to divide by the number of ways to reorder those cards. And we know what that is. We've just done that, is 3 times 2 times 1. And if you work this out, you will get 10. And using choose, using this really nice little mathematical function, you can work out the possibility of different combinations coming up. So for example, if you're playing a game like bridge, you will choose 13 cards from the deck. You'll be dealt 13 cards at random. You can use this to kind of look at what are the chances that a particular set of cards is with a particular player, or if you play bridge, you basically deal the cards into 4 piles of 13 and you each get one of those piles, and there are 4 players, and it's important who's got which cards. Basically, you need to know whether the person before you or the person after has got a particular card, but there are quite a lot of other board games where you do end up dealing out little decks of cards, or you have different cards that you play to do things in the game, and you can use this to sort of look at what are the chances that person's got all the hearts, or this person's got all 3 of the power-up cards, or whatever it is in the game that you're playing. And in fact, as an interesting aside, there's a news story that comes up fairly often. Like, this happens quite often, but this is a news story from a local newspaper about a team who are playing whist, which is a game very similar to bridge, where you again deal 4 piles of 13 cards, and apparently dealt the cards to the 4 players, and they each got the whole of 1 suit out of the 4 suits of cards. They got spades, hearts, clubs and diamonds in their hand, which everyone was completely flabbergasted, dumbfounded, amazed by this happening. I've read the article and I think I've figured out what's happened here, because if you look at the actual chances of this happening, the probability of this happening, they've done various kind of ridiculous odds calculations down here to give you an idea, but it is millions, it's billions to 1 the chance that you would get this exact split of cards. But what it says here is that it was a completely new deck of cards, fresh out of the packet. And if you've ever opened a packet of cards, you'll know that they start off in order like this. So you've got the ace, 2, 3, 4, 5 up to the king, and then the hearts, and then the clubs, and then the diamonds. So they're actually in order already when you start. And apparently they were shuffled twice before they dealt them out. Now, if you do a particular type of shuffle where you take you split the cards in half and then riffle them together, so you end up kind of putting cards in between each other, if you do quite well at that, if you're very neat and you do a good job of it, what you would actually do is just interleave the cards. So if you do that once, you'll end up with hearts and spades in the top half, clubs and diamonds in the bottom half. If you do it twice, you'll end up with a deck that goes heart, diamond, club, spade, heart, diamond, club, spade, heart, diamond, club, spade. So if you then deal that into 4 piles, this will happen. So I think it's still not massively likely, because it relies on you having done it exactly perfectly. But I think someone who maybe wasn't really paying attention to what they were doing took it out and did a riffle shuffle that turned out to actually be completely perfect, and then did the same thing again. And then they cut the deck, so they took the top half and put it on the bottom. That's not going to change it, they're still in the right order, and then dealt out the cards. It is astonishing, as it says here in the article, but I don't think it's quite as astonishing as they think. I mean, unless also the other possibility is they've just lied in order to get in the paper. So, if this guy had the ace of spades and that guy had the 4 of hearts, they would totally have just swapped them and then phoned the newspaper. So this is interesting, but essentially this is one of the things that you can look at. You know what the probability of this happening is. There's no way this has happened by chance. There are just not enough people playing whist, essentially. If there were billions and billions of whist games happening every day, I wouldn't be surprised if this happened more often, but there really aren't. And I think the thing to bear in mind is that one other kind of mathematical thing you can do is you can use what I guess is called information. You can know things about what's happening in the game. So if you're playing bridge like this, you have a hand of cards that you can look at, and the person who's playing opposite you in a game of bridge will put their cards down on the table like they are in the picture, and you can play using the information that you have about which cards you have and which cards they have. And you don't know where the other cards are with the other 2 players, but you can make some educated guesses using kind of probability and your understanding of maths, and you also know that they don't know what cards you have. So you can know that they're making their decisions based on what you know. And a lot of this stuff is applicable in board games. As I say, I play board games with mathematicians fairly often, and you can see the cogs going. You can see that they're thinking about things like this. So I think the thing to bear in mind is that you might actually be doing maths without even realising it. You might be using the same kind of thinking, the same kind of problem-solving skills that you do to solve maths problems in order to actually get better at board games. And I'm hoping that you can maybe use some of the things that I've talked about today and continue to improve and to beat everyone. Anyway, thank you very much.
Thank you. We'll have a quick 5
5-minute Q&A if anyone's got some questions for Katie. If not, follow her on the way round as she'll be wandering around the building.
Yeah, I'm going to be in the STEMettes are doing a panel twice today, so I'm going to be sitting on the panel for that. So if you want to come and see that, it's down. I think it's down on the first floor. But I'll also be around for the rest of the day, and I have blue hair, so you should be able to find me.